All right, we're going to get started. Well, thanks everyone for joining us. My name is Curtis Sherholtz. All right, so today we're going to talk about the brand new Viessmann Vitotron 100 wall-mounted low-temp electric space heating appliance. So you see we got here, it's a low-temp electric boiler with an asterisk. And if you look down here, you'll see it says this appliance complies with UL 834 certification as an electric space heating water heater. A couple of things to look at here on the rating plate. We've got the model number across the top, and then so we have a Vitotron 100 VLN2. Right here is 2-4. This tells us it's a 4 kilowatt version. It's also 4 kilowatt there. The other thing you'll notice is there's two serial numbers. There's a serial number on the top of the barcode and a serial number at the bottom half of the barcode. As far as we are concerned, it is the bottom half or the bottom serial number that we're looking for. This is the Viessmann North America serial number. This has to do with the production facility that Viessmann manufactures the boiler in. That's an internal identification number. But when you're talking to us or talking to tech support or anything like that, or your wholesaler, we're looking for this serial number down here. So just a quick overview of the general specifications. We have the 5 sizes, sorry. We've got a 4 kilowatt, 6, 8, 12, and 14.4. And that gives us a range from about 13,500 BTUs up to just shy of 50,000 BTU. The main appliance voltage for all of the sizes is 240 volt single phase. Now, obviously, the circuit breaker and rated current changes based on the output capacity. So the smallest one has a rated current of 16.66 amps and takes a 30 amp breaker. The largest has a rated current of 60 amps and takes an 80 amp breaker. All of the units contain 3 elements, and we'll go into a bit more detail how those are set up and staged. And then, of course, we have different element resistances based on the size. In addition to the main voltage of a 240 volts that's powering the heater elements, there is also some onboard pump controls, and those will take a separate 120 volt single phase feed that will be fused and rated at 15 amp. One option you have, so the idea is you're going to have to pull 2 separate power sources. One, you could pull 2 separate feeds right from the main breaker panel, a 240 double pull feed and a 115 or 120 volt single pull feed. Or you can do what we've done here in Waterloo in our Academy training facility. What we've done is we pulled a single feed from the panel into this certified panel box. So if you look at how this works, again, the boiler needs to have 240 into the main power. So you got L1, L2 inside the boiler. And then you've got your pump feed, which is an L1 and a neutral. This is all internal to the boiler. So our power comes into this wire panel. We've got an L1 and L2, and we've also brought a neutral in from the main panel. So your L1 and your L2 come up through the disconnect switch, come down, and then are each fused at 30 amp because this is a 4 kilowatt model, so it takes 30 amp fusing, and then pass down to the main terminal connection. So now our main terminal is connected with L1 and L2 fused at 30 amps. We also take this L1 and branch it off through a separate 15 amp fuse, and we bring that to L1 on the pump control board, and then take the neutral back to the main panel. So now we have our main power 2-pole at 30 amps and our pump power, which is single pole 115 volts fused at 15 amp. Again, there is 2 pumps. There is one internal pump that is factory installed and factory wired, and that is a Willow Star S21U15. That's a 3-speed pump. It is a 120 volt pump. At full load, it'll draw 0.97 amps, and it is fused with a 2 amp fuse, and that's a 3-speed pump. Pump 2 is the external circulator pump, and we'll go into some detail as to when you would use that. And that's going to be provided by others, and it is again 120 volt power supply to it. The amps would, of course, be pump specific, although it is again fused at 2 amps. You need to be mindful of that. And the speeds will again be what you select. You could select a single speed pump, a 3-speed pump, or possibly even a delta P pump. We have an operating range, so a supply water set point from 85 to 140 degrees Fahrenheit. We have a manual reset at 194. Our inlet and output thread pipes are 3/4 inch female G-type or British standard pipe thread. We have a built-in expansion expansion tank that is 1.6 gallons. The max rated pressure of the appliance is 30 psi, and it comes shipped with an already factory installed 30 psi relief valve. And we have a minimum operating pressure of 7 psi. This is monitored by an electric pressure transducer, and we'll go into a bit more detail on that. All sizes can have a dry weight when shipped of 68.5 pounds, and all of the sizes are the same physical dimensions of 28 inches tall, 18 inches wide, and just shy of 10 inches deep. And again, we have a minimum flow rate of 1.32 GPM. Taking a look at the actual appliance here itself. So what's really nice is it comes with hinges on the front door panel. So it swings open from right to left. And there's 3 screws holding it in place as well. So you got 2 hinges, and then there's a screw to keep it fastened here. And then 2 screws on the bottom, of course, that would have to be removed before you can open the door. Just a quick overview of what's going on inside this appliance. So what you will see as we go through this is about as close to a plug and play as you're going to get out of a electric space heating water heater. So first off, we've got our wiring entrances, and then we've got our 120 volt pump control board and our main 240 volt control block. We have a 240 volt to 24 volt transformer, and I'll explain what this is doing in the system. We've got a contactor. Well, actually, we have 2 contactors here. Number 4 is the main user interface and logic board. Number 5 is the built-in 3-speed pump. 6 is the built-in pressure relief valve. 7, we get a nice already in factory installed built-in magnetic strainer in the return piping. 8 is that pressure transducer I mentioned. 9 is a built-in automatic air vent. 10 is your 24 volt control fuse. 11 is pointing to your heater elements, so your actual vessel and elements. 12 is a manual reset high limit. 13 is an auto reset high limit. 14 is the power module. This is a triac board, which this stages the elements. For 15 is a flow and leaving water temperature sensor. So it's measuring both flow in GPM as well as the leaving water temperature. 16 is a built-in internal bypass to prevent deadheading of the pump. And 17 and 18, of course, are your connections, your piping connections. So breaking down those components a little bit more each, we talked about having an automatic air vent already installed. So this is a 3/8 automatic air vent. It's located at the top of the heat exchanger, which is nice because this is the highest point of piping within the boiler itself. The other nice thing is it comes equipped with this poly tube, which comes out of the vent, kind of runs down and discharges out the bottom right-hand corner of the boiler. This is nice because then if you are purging air out and it's spitting a bit of water with that, it's not going to spit it onto any of the boiler components or electronics. It'll just discharge out here onto the floor. As mentioned, we have the built-in 1.6 gallon expansion tank. Its pressure is factory set at 14 psi. If you need any additional expansion tanks, you do the calculation and you realize based on system volume that you need a little bit more than 1.6 gallons. That's fine. You can add accessory expansion tanks into the system as needed. At the bottom, you are able to access. So when this is on the wall, you're able to access the Schrader valve to check pressure and adjust pressure of the expansion tank. However, if the expansion tank ever needed to be replaced, it's a pancake type expansion tank and it's at the back of the boiler. So the boiler would have to be taken off the wall. And of course, when we are setting and checking our pressure, we want to do this with the system cold. Taking a look at the relief valve, this is also factory installed. So this is already ready to go inside the boiler. So this is mounted in and rated to be in a horizontal position. It's set for 30 PSI. General rule of thumb, we want to terminate it 6 inches from the floor, and we do not want to reduce the size of or cap the outlet termination. And this is again located right here in the boiler. Built-in pressure bypass valve. So this allows minimum flow rate to pass through the appliance when zone valves are closed. So if you have any zoning on the system and you start closing off zone valves, we can use this bypass valve to make sure that we don't end up deadheading the pump and that we maintain the minimum required flow across the heating vessel. Taking a closer look at how you're going to set this up. Just quick on the right here, you see how this is piped. So we've got our return piping through the pump, pumps it through the heating element and back out the supply to the heating system. Now, if the heating system, all the valves are open, we have full flow, we're going to have all of our flow coming down and in this loop as such. Now, if we start to shut off valves in the heating system and we start to create a greater pressure here than here, eventually this pressure differential bypass will start bypassing some of that excess pressure back to make sure that the pump does not deadhead and that the heating element sees proper flow. So to adjust this, we want to take it and turn it all the way in. So we're going to turn it until it stops clockwise. Then we're going to turn on all the heating zones and let them warm up. The idea here is we want to get warm water in the system because we're going to use our hand to feel when we start to bypass flow in the bypass line. Obviously, be careful because it can get hot fairly quickly. So once we've got it turned all the way in and we're happy that all our zones are open and that the system is warm, we're going to slowly open the bypass by turning it counterclockwise. And we're going to keep doing it until we feel a slight increase of temperature in that bypass flow line. That tells us that we've hit the tipping point where we're starting to bypass a little bit of flow. And then just for good measure, we're going to give it one more full turn. And that way we know that we are starting to bypass ever so slightly, even though the system is full open. So as we close any valves down, that excess pressure will bypass and we won't have a fluctuation through our heat emitters on the system side. Again, we have a factory installed sediment strainer. It's a magnetic filter as well. So we want to make sure that we are just checking this and cleaning this on a regular basis. A good tip that I've had pointed out to me is whenever you get any of these valves, whether you're installing them yourself, filters, whether you're installing them yourself or they're pre-installed in the appliance, it's a good idea before you fill the system to take this cap off, thread it off, put some sort of leak sealant or thread sealant or anti-seize on there and put that back on. That way, when you come back a year or two later, you can actually get that cap off. Taking a closer look at the pipe connections. So what we want to point out here is that these are a 3/4 inch G female or British standard pipe thread. This is different than what we typically use in North America, being NTP pipe thread. The difference is an NTP female fitting will be much longer. This is a shorter socket, and the male fitting is threaded on a taper. And then we use pipe dope or thread sealant or something tape. And as you tighten that fitting, the taper eventually starts to compress in the threads, and the threads is where the actual seal is made. Again, that's in NTP fittings. With these type B fittings, it is a gasket that makes the seal. So shipped with the boiler, it is provided in the box with the outdoor air temperature sensor. You will get 2 gaskets for the inlet and outlet connection. Well, those will go in here, and then you're going to thread the fitting in, and the seal is made at the gasket. And why we want to point this out is if you have to be cautious if you're using just black iron pipe fittings. Those types of nipples tend to have a fairly sharp edge on them. And if you over tighten it, you risk ripping or breaking the gasket. So you just got to be careful you don't over tighten it, or better yet, use a brass nipple that's going to have a bit of a flatter face on it. We find that the brass press fit adapters have a really nice flat face. Or if you want to do it perfectly, you can go out and get a BPST to NPT thread adapter. The other option is Viessmann is actually starting now to stock and offer an accessory flex adapter that will be well fitted to here, and then you can have flex pipe and adapt onto that with your NPT connections down the line. Taking a look at the entire electrical schematic here. So I throw this up. Now I want to go through this here so that as we go through the presentation and start talking about the fixed high limit, the adjustable limit, and the heaters, you guys can kind of have a visual of how the entire system is powered. So if we look at it, we're bringing in our 120 volts here to this pump board. It is completely independent of the main 240 volt coming into the appliance, and it simply is controlling these pumps here. It does come down. This 120 volts does pass down and through a relay in the control panel, which then comes back up and powers the pumps. But this 120 volts is only here to engage the internal and the secondary loop pump if you're using it. Otherwise, we have our 240 volts comes in, lands on the main terminal block. Then from there, you'll notice it comes across and is parallel into these two contactors. And once it enters the contactors, if the contactors are closed, then the 240 volts is passed down to the power unit. And then the power unit passes that power through here down to the main control panel. Why I point this out is I want you to understand that in order for the control panel to get power, the power unit must have power. In order for the power unit to have power, the contactors must have power and must be closed. You'll also see that we have got this 240 to 24 volt transformer. And what this is doing is the safety circuit. So 24 volts is coming out through the fuse, through the fixed high limit. And it is required that this fixed high limit be closed in order for these contactor coils to be energized. So if this fixed high limit opens, the contactors open, this board loses power, and the main board will no longer have power. And again, when I start getting into more of the troubleshooting, you'll understand that a bit better, but just understand that that's the sequence to get power to even the control panel. Taking a look at the ZM63 board. So this is the power module or the triac board. Triacs, just to put it simply, are essentially like a solid state relay. You can look at them just as you would a contactor or a relay as far as how it's actually moving power through the system. So again, our main power comes in, it comes to contactor A and B, and these are in parallel. So L1 here is the same power as L2 here, and L2 here is the same power as L2 here. So L1 comes up, it feeds this at X1, X2, and X3. And then L2 feeds the power module at X4. So this is how the power module gets its power itself between L2 and X3, X2, and X1. Then if any of the heater elements are to be engaged, the associated triac closes. So again, there's always going to be power as long as everything's working and the limit's closed, sitting at X1, X2, and X3. And then as the control tells the power module which elements to engage, it closes that little triac, and then that engages each element through the H terminal. Taking a look at the ZIO50 or the pump control board. So this is mounted in the boiler in the top left corner. It's got your terminal block here. So again, this is coming right from your breaker panel or your control panel, 120 volts, and is fused twice. It sits right here in the top corner. And how this looks internally. So again, your 120 volts comes in on L and neutral. The L comes down and comes out here to this K2 relay, or sorry, K2 output. Now this is still the pump board itself. Now this is all factory wired. It leaves on the K2 terminal and goes out to the main control board where it enters on K2. And the main control board carries a call for pump relay. Anytime the control board determines that the pump should be running, it closes this relay. That 120 volts then gets passed out on K1 back to the pump control board. It comes up, it is split through two separate fuses and energizes pump 1 and pump 2. So the key things here are pump 1 is output is factory wired and the pump is internally installed in the appliance. Pump 2 output is optional and it can be field wired to control a system pump in primary secondary applications. But it's important to note that both pump outputs are controlled by one relay and they start and stop together. So if either pumps one pump starts, they both start, although they are fused separately. So it's possible you could blow a fuse to just one pump, and you have to keep that in mind. And there are spare fuses taped on the inside cover. Now, again, pump 2 is used for optional primary secondary applications. So what does that look like? Well, this is a very simple example of a primary secondary setup. Pump 1 being the boiler pump is circulating water between what we have here as a low loss header. It could be closely spaced teased. So the water is circulating through the boiler as such and through this header. And then on the system side, we have another pump here, which is engaged by the boiler, and it's flowing on the system side of the low loss header or the closely spaced tees. The nice thing here is we could have, say, 3 GPM of flow on this side, and then we could have maybe 4 or 5 GPM of flow on this side, and these are hydraulically separated. So the 3 GPM is going to come this way, all the way and around, and 2 GPM is going to bypass through this low loss header. The internal pump, again, is a Welo Star 3-speed pump. And to determine the speed setting of the pump, you want to do a pressure loss calculation of your system. And then you're going to go into the manual and refer to the residual head tables to determine which pump speed is best for your application. There is an air vent screw on the back of the pump. So whenever you're filling the system or when you first start it or anytime you add water to the appliance or the system, you want to make sure you crack that and bleed any air out of the pump. As defaulted, the pump will automatically operate based on a thermostat call for heat. So the thermostat closes, tells the appliance that it needs a call for heat. The pump is started. Pump runs the entire time the thermostat is closed. Then the thermostat satisfies, it opens up, and the pump will run for an additional 20 seconds to purge any extra heat out of the vessel. Now, again, that's the default operation. As we go through the system configurations, I will show you how you can set the pump to run all of the time. So the default is automatic, starts and stops with the thermostat. Another option is to have the pump run all of the time. Here's just an example of this residual head table. In the manuals for this particular boiler, they call it disposable head. But if you're familiar with the Viessmann terminology, we call it typically residual head. At the end of the day, this is the amount of available head you can get out of that pump after it satisfies the appliance itself. So you don't need to worry about what the pressure drop is in the appliance. That is already taken into consideration with this table. This is simply what is left over after that. So if you were looking for, say, 3 GPM of flow and at 8 feet ahead, well, speed 2 will get you there just nicely. It'll be in the knee of the curve. We do have a flow sensor and leaving water temperature sensor in one. So this particular device is performing 2 functions. It's got a 6-wire ribbon cable here. What you'll notice though is there's 3 wires here and 2 here, and one is snipped off. That's okay. That's how this is supposed to be. These particular controls are used in many different applications, and in some applications they use this extra wire. What's nice though is it's got this ribbon cable here, and the 2-wire plug and 3-wire plug are separated, so you can't mix them up. There's no way to flip the flow and the temperature out incorrectly. The temperature sensor is a 10K NTC thermistor. There's thermistor curves in the service manual if you need to troubleshoot that sensor. Of course, the flow portion connects to flow, and the T out is the temperature out sensor. We also have a pressure transducer or a pressure sensor. And this is, again, factory installed, and it reports back to the terminal labeled pressure. The minimum allowable pressure to operate the appliance is 7 PSI. If you're under that pressure, the heater elements will not be able to engage. Just be mindful that this is a wet connection, okay? So this sensor, there's no Schrader or anything behind that. Once you thread that off, the water that's in the boiler is going to come out, so you have to drain the appliance first. What you will see, though, is it is right at the bottom in a nice low spot, so there shouldn't be too much residual water. Obviously, you want to expect that there's some residual water after you drain the appliance. Definitely whatever's in here. And the other nice thing is it's right at the bottom here. So even if there is a bit of water, obviously you still want to try to catch as much as you can, but you don't have to worry about it dripping on any of the appliance electronics. So just taking a closer look at how some of the power and communication is passed along the different modules within the appliance. So as I mentioned, as long as the contactors are closed, the ZM63 or the power module gets its power. Then from there, it outputs power on the output into the main control board on terminals L1 and L2. In addition to main power being passed from the ZM63 to the main control board, communication also takes place between the TRIAC board and the main control board. So basically this main control board's looking at all these inputs, it's looking at all these sensors, and it's telling this power module which of these TRIACs to close and which heater elements to engage. There is also an automatic reset. This is a high limit, automatic high limit reset. It trips at 40 degrees Fahrenheit, and it reports directly to the ZM63 module. So what's important to note here is if this limit opens, the main control itself doesn't know that this limit's open. So it'll tell you that there might be a call for heat and the pump will be running and everything like that. Where you got to look at is the LEDs that are on the TRIAC board itself. So you'll see, hey, there's supposed to be a call for heat. It says that I have at least one element running, but none of the LEDs are on. Then you're going to want to go and check this auto reset limit, because this is basically just as soon as this opens, all of these TRIACs are forced open. We've also got the manual reset high limit. So you notice the auto reset limit trips at 140 degrees, manual limit trips at 194 degrees. So quite a bit higher than the auto reset. And again, power is coming from the transformer through the fuse, through the manual reset limit, and that engages the contactor coils. So if this transformer is to fail, or this fuse is to open, or if this manual reset opens, then the contactors will open, then the ZM63 board won't get power, and the main control won't get power either. If this opens, and we'll go through a little more detail later in the presentation and troubleshooting, but if this limit opens, you should really be looking at why that happened, because really the automatic limit should have tripped long before the boiler vessel temperature got to 194 degrees to trip this limit. And we'll talk about some reasons that that could still happen and the significance of why these contactors are in here. We have a return water temperature sensor as well. This is obviously mounted in the return piping, and it is again a 10K NTC thermistor, 10K NTC thermistor, and it is connected to temperature in. Just a quick look. So you have your return water comes up, down, and then you'll see there's a bit of a flange on there's copper soldered to the return pipe, and it sits right on top of this ZM63 or TRIAC board. It's literally sitting right on top of the TRIACs. The idea here is that the return water can help provide cooling to the TRIAC board. So if these start to heat up, the return water can help cool off that board, and then any waste heat from the TRIAC board can also be projected into the return water, and you'll see our return temperature sensors mounted right there. As far as your field control voltage terminals are concerned, we've got the off-peak control. So this is OP. This is factory jumpered. And what this is meant is a dry contact. So it's not there's to be no voltage applied to this contact. Again, it's factory jumpered. And if you want to maybe use a timer or have a utility curtailment signal sent to the appliance to stop the appliance from working, you can use this terminal. So again, the appliance will be allowed to operate if it's closed, and if it's opened, then it will block operation of the appliance. We've got the thermostat, which is fairly self-explanatory. This could be a conventional 2-wire thermostat. It could be end switches from a zone valve or a control panel. And it, again, must be voltage free. So this is a dry contact, just like this is a dry contact. And you can use just standard 18 2 thermostat wire. There's plenty of 1/2-inch knockouts available on the side of the appliance. Obviously, using proper electrical practices, we don't want to pass our control voltage through the same knockout that we're passing any line voltage through. Use a separate knockout, and then install the thermostat in an appropriate location where it's not going to be influenced by any heat sources. So there's not a window that's going to shine light on it. There's not a water cooler right underneath it, or even a panel rat or anything like that. Got to put the thermostat in a good location. So again, you've got the OP and the thermostat. In reality, how this works is both of these have to be closed in order for the boiler to produce heat. This one is meant to be an operating control of the system, and this is a utility curtailment control. We've also got an outdoor air temperature sensor. This is, again, a 10K NTC thermistor, and there will be appropriate thermistor curves in the service manual. When you hook up, the second this appliance sees a sensor connected to OAT, it automatically goes into a outdoor reset operation or a weather compensated operation. So we want to make sure that we're installing the sensor in a good location. It's going to be above any potential snow lines, preferably on the north side of the building. We don't want it to get any direct sunlight that's going to give it a misread. We want to make sure that it's not near a dryer vent or an HRV vent or anything that's going to give it a misread. And a little tip that we were given by the appliance engineers, which I think really makes sense, is, as I mentioned, the second you connect an outdoor air temperature sensor to here and the appliance sees that, the appliance immediately configures itself to work off of heating curves. And we'll go through some detail on how the heating curves work, but essentially the warmer out it gets, the lower the boiler water temperature goes, the colder out it gets, the warmer the boiler, warmer the boiler water temperature goes. What they had pointed out to us, which makes sense, is when you first install this appliance, don't connect the outdoor temperature sensor right away, because then the appliance will look for a fixed set point. Go into the control and give it a fixed set point that you would want the boiler to go to in the event there was a failure of the outdoor temperature sensor. So you're going to not connect it, go in, program an appropriate fixed set point, then hook up the outdoor temperature sensor. This way, if there's ever a failure of the outdoor temperature sensor, maybe it takes a hockey puck or something and it gets destroyed, the boiler will then go back to what you programmed as the appropriate fixed set point. And that, of course, is connected to the TX. We want to make sure that we are being very cautious when we're sizing these appliances. We don't want to massively oversize the appliance, because that just creates waste and it could short cycle, as well as it's just a waste of materials. So we want to select the size of the appliance. So these are rated in kilowatts, and you're most likely going to get your heat loss in BTU hours. So we just do a simple conversion to convert BTU to kilowatt. And as mentioned, we don't want to massively oversize it, nor do we want to undersize the appliance. So take a look at a quick example here. So in this example, we are going to say that we had a heat loss of 36,000 BTU. Now, again, we got to convert this into kilowatts, because that's how our electric appliances are rated. So we're going to take that 36,000 and divide it by 3,413. And that tells us we have a heat loss of 10.5 kilowatts. So we don't want to be any less than 10.5, but we don't want to be any greater by more than 20%. So we take that 10.5, we times it by 1.2, or 120%. And that tells us that the appropriate appliance kilowatt rating should land between 10.5 and 12.6 kilowatt. Well, if we look at the 8 kilowatt option, that's obviously under the 10.5 kilowatt. If we look at the 14.4, we're over by more than 20%. We're over our 12.6. And if we look at the 12 kilowatt, it lands us in there nicely with a BTU rating of 40,956. So just a little quick way to make sure that you're not over or undersizing the appliance. For any larger loads, you could consider cascading the appliances together and piping the system in parallel. So remembering we have a size that'll go up to just shy of 50,000 BTU. So by putting two together, you can get yourself up to about 100,000 BTUs of capacity, or anywhere there in between. When you're doing this, though, it's important that you use a third-party staging control. So the third-party staging control is going to stage the boilers, and it's also going to stage the system pumps. So these are the pumps on the system side of the low loss header. Breaking down the HMI, or the human machine interface, we have a bunch of LEDs on here, as well as a 7-segment LCD display with 3-digit positions for that display. So how this works is there's all these LEDs will light up depending on the view mode you're in. So we have one for, which is 100 times British thermal units per hour. So when this LED is displayed, whatever's on here is British thermal units times 100 is the current output of the appliance. We've got a pounds per square inch, a GPM, which is your flow rate. There's a Fahrenheit temperature light. How this one works is, as you go through different sensors, any sensors that the display would be related to temperature, the Fahrenheit will also engage. So as an example, this is entering water temperature. So if I scroll to this and this LED lights up, whatever is on the display is the inlet temperature in degrees Fahrenheit, and that will light up. As where if I went to say PSI, that's not a temperature rating, so the Fahrenheit LED would not be engaged. Again, we've got an appliance operation, call for pump status, temperature outlet. So the triangle or the arrow leaving the box is outlet temperature, and the arrow entering the box is inlet temperature. And the home can be call for heat status. There's also a couple LEDs right on the circuit board itself. Pump is fairly self-explanatory. If this LED is on, that means that the pump relay is closed. TT is thermostat. If this LED is illuminated, that means the thermostat contacts are closed. And OP, if it is illuminated, that means the off peak or the OP contact is closed. There is additionally this stat one, and this one is basically a status indicator that the board itself is functioning properly, and it'll just blink a green LED kind of somewhat randomly and let you know that the board is communicating with itself and everything's okay. So in addition to these LEDs, we've got 4 buttons. We've got a power button, we've got up and down, and we've got a scroll option. You're going to utilize the push buttons to scroll through different working menus. What you will notice, or the first thing I noticed once I started playing with this display, is there's no enter button, okay? So you scroll through until you find the setting you want, and then it'll appear on the display, and you simply just press up or down to adjust that setting, and then scroll to the next setting. There's no enter or save button required to be pressed. And if no buttons are pushed after 1 minute, the control will automatically switch back to the main view. And this here is the main view. So right now on this main view, we can see that the pump is engaged. The current displayed temperature is the outlet temperature. So whatever's on this display is the outlet temperature in degrees Fahrenheit. And the green LED next to the house tells us that the thermostat's closed, and the red LED tells us that the heating elements are engaged. So again, taking a look at the house, this could have 3 positions. If this LED is off, it means the thermostat is open and there's no call for heat. If this LED is blinking green, it means the thermostat's closed, but the OP terminal connection is open, so it's being blocked by off peak, okay? And if this LED is illuminated and solid green, it tells me that the thermostat's calling for heat and the OP terminals are closed, so it is able to heat. We've got the internal circulating pump indicator. So for this one, it could be off. If it's off, it just means that the pump is not calling, nor should it be calling. If it's on, it means there's a call for pump and all is well. If it's blinking, it means there's a call for the pump However, the built-in flow meter is not measuring adequate GPM. So this is saying the pump should be running, however, the flow meter is not seeing adequate or sufficient flow. Could be a failed pump impeller, could be a blocked system, lots of things could go on there. So it's giving a little bit of feedback as to what's going on. Supply water temperature is indicated by this radiator here. So in the main display, if this LED was off, it would mean that there is no call for heat. If it's green, it means there's a call for heat, but the boiler water leaving temperature is already at or above set point. So there's a call for heat, but the water's at set point and none of the elements are active. And if it's red, that tells us that there's a call for heat and boiler water is below set point and at least one or more elements is actively heating the water. We have a supply water view. So you can scroll to this and you'll see the view. And this is going to appear in one of two ways, depending on whether you're using outdoor reset or not. So if you come into the supply water set point and you see the display and it's got a temperature here with a red dot in the bottom right corner. The other thing we'll notice is you can't make adjustment. You'll hit up and down and the number will go nowhere. But the key, what you're really looking for is this red dot in the bottom right corner. If you see that, this is telling you that whatever the current set point is calculated based on the outdoor reset temperature curve that you have set up. If you come to this and there's no dot, you will notice that you will be able to push up and down to change it. And if there's no dot, that's telling you it's a fixed set point. It is not going off outdoor reset curve. Whatever is on the display is what you set it to based on the up and down arrows in the range of 85 to 140 degrees Fahrenheit. Return water indicator, as we mentioned before, the arrow entering into the box is return water. And because what it is showing you on the display is represented in degrees Fahrenheit, you will also have the Fahrenheit LED illuminated. Supply water is the same, except it is represented by the arrow leaving the box. GPM, fairly self-explanatory. If you scroll through the LEDs and it lights up next to GPM, whatever is on the display is the current gallons per minute flow rate. Note that there is a decimal place. PSI is the same. Scroll through and get the LED next to PSI to illuminate. Whatever is on the display is the current level of pressure in pounds per square inch. And again, note the decimal place. Energy consumption view. Again, you scroll through and you get the LED next to the 100 times BTU hours to go green. Whatever is on the display is telling you current energy consumption in BTU hours times 100. So for example, we have 477 displayed on the display. Well, times 100, that tells us the output is 47,700 BTU hours. So you can view this, and this will help you see how the appliance is staging. If it's at 100%, if it's at 33%, 66%, or somewhere in between. We also have an outdoor temperature view. So the outdoor temperature view, it does pony itself, or it borrows the LED that is next to the thermostat call. So when you're in the main display, this is telling you that if the thermostat's calling. Once you're in the data views display, if the LED next to the house is on, of course, the Fahrenheit symbol will be on as well. And that's because what is on the display is your outside air temperature in degrees Fahrenheit. So what they're talking about here is summer mode. And what they're saying is it's important to not shut the power off between seasons. So when you get to the summer and you don't want the boiler to run anymore, don't turn the whole disconnect off. The reason for that being is this will start the pump for 15 minutes every day, even in the summertime, and this helps protect the appliance and the whole hydronic system from having any sediment or sludge or silt build up in any one spot. So instead of shutting the power off, just go to the main disconnect power off, go to the actual display, press and hold the power button for 3 seconds. The display will go blank with the exception the dot LED in the bottom right corner will blink every few seconds. So in this mode, the appliance is off, but as mentioned, the pump will be activated for 15 minutes every day to prevent things from seizing up or building up in any one spot. Now, what's important to understand is that if this is done for 15 minutes every 24 hours or every day, and the time it does it every day is based on when you actually enter this mode. So if it's important to you for whatever reason that this 15-minute pump sequence, let's say it needs to happen at 10 a.m. every day, well, then it's at 10 a.m. one day. You have to go and press this button for 3 seconds. And then for the rest of the summer, until you turn it back on, it'll cycle that pump for 15 minutes starting at 10 a.m. each day. And for what it's worth, if you look at a electrical rate of 10 cents per kilowatt hour, operating the pump for 15 minutes a day will equate to approximately 8 cents of electricity per month if the pump is in the highest speed. So if you have a customer who just doesn't want to waste any energy, you got to explain to them that any additional maintenance costs incurred by not stirring the water on a regular basis and preventing the pump from seizing, they're going to massively exceed that in maintenance costs. It's better to just use the 8 cents a month worth of electricity. To get into the advanced settings, or maybe you would call those the installer option screen, you're going to follow the following sequence. So you're going to first press and hold the power button for 3 seconds and release. This puts it into the summer standby mode that I just talked about. Then once you're in the summer standby mode, you're going to press and hold the right arrow button and immediately press the power button and release them both. And what will happen is the display will go blank for a second. It'll populate, it'll go blank, and then you'll see a P and either the number 4, 6, 8, 12, or 14 will appear. And I'll explain why that is on the next slide. And again, then you're going to, so now once you see that P plus whatever number, you know you're in the parameter mode, the extended parameter mode, and you can scroll to the next parameter by pushing the right arrow or adjust the current parameter setting by pushing up or down. And then you press and hold the power button to exit and save settings once you're done it all. You don't have to do this between each setting, to be clear. There's about 12 or so settings. You can go in and set each one where you want it, then press the power button. It'll hold all those settings. So why I mentioned that the first thing you will see is a P followed by either 4, 6, 8, 12, or 14 is because the very first parameter, parameter 1, is appliance power. So this is a factory set value and you shouldn't need to change it. You just want to make sure that it matches the kilowatt rating of your appliance. So if it's a 4 kilowatt, you should see a 4. If it's a 12 kilowatt, this should be a 12. The reason this is in here is because maybe one point in time you'll have to replace this main display or the board, in which case it'll be a generic service part for all the sizes, and you'll go in and program this appropriate to the appliance size you have. So assuming this comes up and it's correct, you're going to scroll to the next setting. Number 2, you're going to see a P in the middle segment and then either an A or an N. The default is automatic, and this is what I was talking about, where you can set the pump up to follow a automatic program, which anytime the thermostat closes, the pump starts. Anytime the thermostat opens, the pump continues to run for 20 additional seconds and then stops. The other option is you could change it to N, so it'll be a PN, which is manual or continuous duty of the pump. The pump just runs all the time unless it's in summer standby mode. Option 3 is the maximum quantity of active heating elements. All of the 5 sizes we have, the 4, 6, 8, 12, and 14.4, all have 3 elements. You will always have this set at 3. And that was where it will default. Option number 4 is whether you are using the PSI indicator or not. You could turn this off. I don't know why you would want to. You could. And for what it's worth, if you shut this off, then the appliance will not stop when the pressure goes below 7 PSI. So you negate that safety feature. However, the flow meter will still be looking for a minimum flow of 1.1 GPM. So it will still stop the appliance if it doesn't see that minimum flow. My recommendation is you leave this on. It should be on. It's defaulted on. Leave it on. Parameter 5, this is the outside temperature above which the appliance will not heat. So if you're using an outdoor temperature sensor, you can set essentially what we call a warm weather shutdown. So if I was to set this value to say 60 degrees Fahrenheit, as soon as the outdoor temperature sensor reads a value above 60 degrees Fahrenheit, regardless of whether the thermostat is calling, the appliance will not heat. It's warm weather shutdown. Your options are 30 to 70 degrees Fahrenheit or off. And of course, if you're not using an outdoor temperature sensor, it's defaulted to off. Off meaning that no matter how warm outside it gets, the appliance will still be allowed to heat based on a thermostat call. Option 6 is your heating curve or your slope, and you have options of 1 through 9 with the default being 4, or it will be 0 if you are not using outdoor reset. In addition to slope, we have an offset, which in the Viessmann terminology is a shift, and I will show some graphics to explain this a bit better. And lastly, we have number 8. It is the radiator with a red LED, and this is appliance working counter in hours, so the amount of time it's actually been heating. This will be displayed, it'll show 1 digit at a time, but it may kind of flash 2 digits. So as an example, if you went into this mode and it said 39, 39, that's telling you that the hours is 39 hours. So taking a little bit deeper dive at the heating curves, again, as long as you have an outdoor temperature sensor, it's going to look to follow one of these heating curves. The default is 4. You can pick curve 1 through 9, and you can do up to 9 degrees negative shift or up to 9 degrees positive shift. So how would that look in the actual programming? Well, first you're going to go to HC, and let's say you set it to 4, which is the factory default. That's going to pick this curve. Then you're going to go to the next option, which is the offset. It's going to be defaulted at 0. If it's defaulted at 0, it's going to follow this red line here. But if I wanted to increase or decrease that curve by either up to +9 or -9, I can do so. Here's an example of it being -9. Here's an example of it being +9. So with this example, if I picked heating curve 4 and I gave it a shift of +9, if it's 20 degrees Fahrenheit outside, I'm going to get about 132 degrees supply water temperature. Let's say the temperature increases. Now it's 50 degrees Fahrenheit outside. I'm going to get about, let's call that 104 degrees boiler water temperature. So the colder out it gets, the warmer the boiler water temperature goes. The warmer out it gets, the colder the boiler water temperature goes, and you can adjust the slope and the shift. Some quick troubleshooting. If you come up to the display and you see 3 E's, this is basically saying that something is corrupted on the main display. You probably want to phone tech support and just run it by them. They may have some quick checks that you can do. Odds are you're going to end up replacing the main control board. If you scroll through any parameter, so as you scroll through the parameters and you see dash, 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 that's telling you that the range of that sensor is failed. So I scroll through and I enter the parameter that shows me the arrow exiting the box. If I see dash, 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 well, the arrow exiting the box is the leaving water temperature. That's telling me that the leaving water temperature sensor has failed. If the display is completely blank, well, that means you likely don't have any power, at least to the display. So that could be simply you have no power directly to the appliance, or it could be that the manual reset's open and it's the contactors are not passing that power down to the ZM63 or the power module. And if the power module doesn't get power, it can't send the power to the main display. If the PSI indicator is blinking, what this is telling you is that the system pressure is less than 7 PSI. So if it's less than 7 PSI and it's enabled, then the boiler will not be allowed to heat. So you're going to need to figure out why the pressure is low, correct that, and then top up the pressure. Now, to be clear, if it's blinking, that means the sensor is good, but reads a reading less than 7 PSI. If you come to this and it's the 3 dashes, that's telling us that the sensor itself is faulty. Pump indicator. So this is the pump status indicator. If it's blinking, so again, if it's on, pump is on, everything is well. If it's off, there's no call for pump. If it's on and blinking, it means there's a call for a pump. However, the flow meter has not seen the minimum required flow of 1.1 GPM per minute. So that could be Maybe the impeller on the pump is broken. Maybe there's a blockage in the system. Possibly the pump fuse has blown. There's a lot of things that could happen. But if you see the pump indicator blinking, that is an indication that the boiler is telling the pump to run, but it is not sensing that the pump is running. Taking a look at the house icon, again, it could be off. Off means that there's not even a call for heat. It could be on all the way. If it's on green, that tells us there's a call for heat and the OP terminal is closed. And if it's blinking, that tells us the thermostat is closed, but the boiler is being blocked because the off-peak signal is open. So again, looking at that flow meter and pressure transducer, all of these components in here, as well as just general system maintenance, is just a reminder why it is very important that we regularly service this strainer and magnetic filter. By keeping this in good condition, we keep debris and sediment out of the boiler itself, and we can keep the proper functioning of the pressure transducers as well as all of the other system components. So we want to make sure we're cleaning this at least annually. So very basic troubleshooting. So let's check to make sure that we have the proper power into the boiler. So it should be 240 volts. We're going to take our meter, put it on L1 and L2. If it is correct and everything is good, you should see 240 volts or whatever the feed voltage to the appliance is, as long as it's within the appropriate range. So that could be as low as maybe 205 volts, or it could be 248 volts, as long as it's within the appropriate range. If no voltage is measured, then you want to check the main disconnect to make sure that it isn't off, or the circuit breaker to see if it hasn't tripped. And remember that this circuit powers all of the all of the components within the appliance with the exception of the pumps. So if you don't have power here, then you're not going to have power on the display itself. Now, if we take a look at how we're going to troubleshoot and make sure we have appropriate power to the pump module board. Again, we're going to measure from line to neutral, and we're looking for 120 volts. Again, that could be 110 volts. It could be 124 volts, as long as it's within the appropriate range. If we have no voltage there, then we want to go back to the disconnect or the breaker and make sure it's okay. In addition to measuring that you have 120 volts between L and N, I would recommend measuring that you have no volts between N and ground. And what this just does is make sure that you don't have your polarity switched here. The 120 volt potential should be from L to ground, not neutral to ground. So again, just make sure you have 120 from L1 to neutral. That's good. And make sure you have 0 from neutral to ground to confirm that you don't have the polarity switched up. And again, this powers P1 internal pump and P2 external pump if used. And the 120 volts is fed from this board through a relay in here and then back up. Taking a look at the automatic reset. So this is a normally closed contact and opens at 140 degrees Fahrenheit. If it's open, what you want to do is shut power off to the appliance, use an ohm meter, and ohm across. You can leave this connected. I've tested this myself. You just shut power off. You can ohm across, and you're looking for 0 ohms or very close to it to indicate that this is closed. If it has infinitive or open lead, that's telling you it's open. You need to wait for the temperature in the vessel to cool back down below 140 degrees, in which case it should reset. Now, keep in mind that any limit has a hysteresis. So if this opens at 140, it may not reset till, say, 120. So you want to wait for it to cool down nice and cool before you determine that that switch is stuck open. Now, if you let that cool right down to, say, 80 degrees Fahrenheit and that switch still doesn't reset, that tells you that the switch has failed, it's stuck open, and you're going to want to replace the switch. Checking the control transformer voltage. So first things first, let's just check right at the transformer. I should have 24 volts-ish between common and my 24 volt out. Again, this could fluctuate. It could be 22 volts. It could be 26 volts. What's important to note, though, is on the transformer, we have a common tap, a 240 tap, and a 208 tap. If you measure this here, and let's say it's all the way down at 18 volts, well, it's probably because your supply voltage into the appliance is only around 208 volts. So you're going to want to take this, move it from the 240 tap to the 208 tap, and then measure here, and you'll see that your control voltage is back up into the appropriate range around 24 volts. So again, good transformer, common to 24 volts, you should measure approximately 24 volts. If there is zero, so now we're going to take a look at going after the fuse. So if you measure from common, so you can see we got common, 24 volts out, it's coming up here through the fuse. So if you measure between common and the outlet of the fuse, if you've got 24 volts, that tells you the fuse is good. If you got 0 volts, that tells you that the fuse is likely open. In the event that the fuse is open, or you measure it as open, or not, sorry, open, you measure 0 volts on the outlet, telling you there's a pretty good chance that the fuse is open. You want to just double check that by turning power off to the system and ohming across the fuse itself. If it's a good fuse, you should have 0 ohms of resistance. And if it's a bad fuse, this will read OL, or open lead. So assuming you've confirmed that the transformer is good and that the fuse is good, next thing you want to do is check that you're getting power all the way through the wiring to the inlet of the high limit. So we're going to measure again from the transformer common to the wire entering into the high limit, and we should have 24 volts. Then we're going to measure the power coming out. Now, when we get to the outlet side, if this limit's closed, we should expect to have 24 volts. However, if it's open, we're going to expect 0 volts. If it's open, that means that the system has overheated this vessel to the point where it has gone past the 140 volts that the auto reset limit should have tripped, continued to rise, and tripped the manual reset limit at 194 degrees. I really want to stress that if this limit trips, you should really be looking for something wrong. If everything's working properly, even if the system just overheats, this auto reset limit should trip long before this manual reset limit trips, okay? And as we go through, I'll show you a possibility of what could happen to cause this manual reset to open. Again, this limit should not open under normal conditions. We want to investigate why it has opened. When we're measuring the triax, we're going to confirm the condition of the triax. So we're going to measure this right on the ZM board, and we're going to be taking the L2 measurement from the leaving triac terminal. If we expect that the triac is closed, so that we think it's closed and it should be closed, then we should measure 240 volts across the element. If we expect that the triac is open, meaning it's not calling, then we should measure 0 volts across the element. Now, if we expect that the triac is open, yet we still measure 240 volts across the element, we want to replace the power module. This is telling us that we have a failed triac that's stuck closed. So that's one possible way you could overheat that vessel, is if you had a stuck closed triac. And just a quick visual of how you can make those measurements. So again, L1 is parallel to L1 here. L2 is parallel to L2 here. L1 is feeding the X terminals, X1, X2, X3. L2 is feeding the return side of each element, or the common side of each element, with the exception of element 1, which first comes up to X4 on the board and then goes back to L2. The nice thing about this is we've got an L2 terminal, and then we've got L1, 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 and we have each triax output as H1, H2, and H3. So we can use this to kind of hopscotch along. So if I measure from here to H1 and I have 0 volts, that tells me this triax open. If I measure from here to H1 and I have 240 volts, that tells me this triac is closed. And you can just hopscotch along the whole way and check each of those out. Now, another reason, so one reason you could overheat the vessel is if you had an actual failure of a triac. The triac stuck closed and it just keeps giving heat to the element, and eventually it pops that limit, and which opens the contactor and kills power to the whole system. The other possibility is you could have a leaky element where the resistance, the shielding or the insulation on the element is breaking down and it's allowing some voltage to pass to ground. And we can check this with a megger. And basically, we want to have a minimum resistance of 2 mega ohm. As long as the resistance from ground to each of these elements, ground being the actual shell of the vessel, to each of the elements is greater than 2 mega ohms, it should be good. If it's less, you're going to want to replace the vessel. Now, again, you can't replace just the elements on their own. Any element fails, you replace this entire vessel as an assembly. So just to give you an idea, the triac is in L1. So this opens and closes and under normal circumstances interrupts the circuit. If this opens, power can't continue through. But L2 is always closed as long as the contactor is closed. And from L2 to ground, you're going to have 120 volt potential, at least in North America with the vast majority of power systems in a residential application. What can happen is even if the triac is open on L1, if you have a leak to ground, remember you have 120 volt potential from L2 to ground, you can have a portion of the element being powered with 120 volts to ground. So even if it's just halfway through this element, it's halfway through the element and it's half the voltage, but eventually that's going to be enough heat if the pump is not running and the system's not calling to raise that temperature. And it doesn't matter if the automatic limit opens, because the automatic limit only opens this triac. It eventually has to raise to as high as 194 degrees, where it will trip the manual reset limit. The manual reset limit interrupts the 24 volts to the contactor, which kills power to the whole system, and the system is safely locked off at that point in time. Take a look at some of the more basic piping layouts. So in this particular one, we're looking at a one heating loop downstream of a low loss header or closely spaced tees. This is a primary secondary application. So this pump could be controlled by the boiler on the P2 outlet, and this pump is P1. Anytime the thermostat closes, both pumps start and the boiler starts to heat up water. And even if there's a different flow rate on this side than this side, that's okay because we are hydraulically separated. Again, both pumps are fused at 2 amps. However, if you've got a pump on your P2 side and you're starting to exceed 1 amp, that's the point where you're going to want to start considering using a pilot duty relay. So use the P2 outlet from the boiler to close a 120 volt coil on a relay, and then you can pick a relay and power source that appropriately matches the power requirements of your pump. In this particular example, we are not using any hydraulic separation, and we've got 2 heat emitters. So in this case, we've done our frictional losses. We've looked at the residual head, and we said that the boiler pump itself has enough residual head to handle the entire system on its own. It doesn't need to be hydraulically separated. So what we want to do in this case is likely add balancing valves. We want to put in balancing valves so that we can control how much of the flow goes through one emitter versus the other emitter. The other option is to just do a reverse return piping, where the first one in is the last one out. However, balancing valves is going to give you the most control. Now we're taking a look at having 2 heat emitters where each emitter has its own pump. Once we get into this situation, in order to control these pumps separately, we're going to have to relinquish control of the system side pumps from the boiler and use a third-party control. Now, this third-party control, let's say this system has a thermostat, it tells a third-party control that it wants heat, it's going to engage that pump, and it's going to send a signal out to the boiler to tell that this dry contact is going to close the thermostat connections and tell the boiler to produce heat. Now, each of these pumps can run independently. Anytime there's a call for heat at the appliance, the boiler pump starts. Example 4, we're looking at primary secondary with 2 boilers. So let's say we needed a heating load of 70,000 BTU. Well, we'd have to use 2 boilers or 2 electric boilers to achieve that. And again, we're going to use the third-party control. Pumps are going to be staged by the third-party control, and the third-party cascade control is also going to stage these appliances based on leaving water temperature. So it's going to have a set point. It's going to be measuring leaving water temperature, probably right in the low loss header. If the leaving water is dipping too low with just one appliance running, it will stage up the second appliance to satisfy the requirements. That is that. Again, thank you for the time with us and taking a look at this new Vitotron 100 wall-mounted boiler. First thing I noticed when I saw this boiler is how plug and play it is. There's so many built-in controls ready to go. You really just have to hang it, pipe it, and hook up a system pump in your piping if that's the way you're doing it.